All right. Last time we did particle in a ring. I repeatedly called it rigid rotor, which is what we're doing today. You'll see how they're very closely related. But we put this restriction on it. We're essentially doing another form of translational motion that's going to give us this idea of angular momentum, because we've got something that's constantly moving in a circle. So the momentum is not in a straight line now, it's kind of in a curving path. And we're going to have to talk about how we deal with that. When we did the particle in a ring, we really didn't have to deal with that terminology yet. We said the Hamiltonian is going to be the momentum operator squared, which we can rewrite with the Laplacian, which is just the generic like d by dx squared, d by dy squared, d by dz squared. In this case, the z dropped out because we were limiting ourselves to the xy plane. And we said that gives us, if we rewrite this, because the way that x and y are related to each other, we can rewrite it in terms of r, theta, and phi, and we get a little bit of simplification. That simplification makes it so our Hamiltonian looks shockingly like the particle in a box Hamiltonian, which didn't surprise us because we got ring, we got box, we got ring, we got box, right? If you just take the ends of the box and you wrap them around to each other, you're essentially doing a ring. But it does change your boundary conditions. Now instead of being between 0 and L, it's 0 to 2 pi, where it loops back on itself. And so we had that condition of at any point, if we're at some theta, and then we go around 2 pi back to that same theta, we have to get the same value, right? In order to have our functions be well-behaved, we need those single-valued functions. And that gave us a restriction on our m sub L values. It gave us a wave function that we could write down that was relatively simple. And you can do it for the e to the im phi or e to the negative im phi, because the m sub L flips back and forth anyway. And we got some m sub L, we got some energy related to that restricted number. And the particle in a ring is really just a baby step into talking about the rigid rotor, because it simplifies our dimensional, this is the simplified dimensional analysis, we'll see. And it just kind of gives it doesn't have a lot of applications though. You can use it to relate to some cyclic compounds and talking about electrons in a conjugated pi system like a benzene ring, or a couple other examples. If you're doing the homework in the textbook, they have like 2 or 3 different examples. They use something from chlorophyll as one of their examples as well, because you've got that kind of cyclic system where you've got that particle moving around in that electron in the delocalized pi orbital system being able to run along that circle. And so you can kind of use this to model that. But if we really want to talk about things that are rotating in 3-dimensional space, we have to take off this false restriction of being stuck in the xy plane. And we have to go to true 3-dimensional rotation. Questions so far? Okay. So what I'm going to do now is I'm going to tell you where we want to end up. I'm going to tell you the things that by the end of the class, you'll look at these things and be like, oh yeah, that's useful. Right now, it's just going to look like random information. But for the rigid rotor, we end up with a similar but different system. Our Hamiltonian is going to be equal to angular momentum squared divided by 2I. And as a reminder, I is going to be the reduced mass times r squared. In the cases where you see it as just mass times r squared, that's a theoretical single particle type system. We're often going to be looking at diatomics or larger, so we're going to have reduced mass, some like diatomic molecule tumbling around in space. We've got our Hamiltonian. We are going to have energies associated with this that are going to depend on some quantum number L, some restricting counting number. Those energies are going to be easy to calculate if we know what L is and how L is restricted. It's just h bar squared over 2I, L times L plus 1. Kind of similar to other things we've seen, h bar squared over 2I times something. Our L values are restricted. L can be 0, 1, 2, 3, 4, 5, 6. there is a function associated with this. Oh, I forgot to bring something. It's okay. Those functions, we actually use a different symbol for them because the wave functions we're going to have are called spherical harmonics. They are very well studied. Once we look at how we set up this problem, you'll probably be like, yeah, I don't want to solve this either. Let's just use the answers that are already there, which are the spherical harmonics. I handed out one of the pages I handed out on the first day of class. I meant to bring my copy with me today. Is the spherical harmonics. So if you pull out your handouts from the first day, you're going to get this function that depends on theta and phi that we get from a table. There's two other things that are useful here. We can get a z component. I keep flipping my L and my M somehow. This last bit, where did I put it? Right, where these spherical harmonics, the reason we use these special functions is because they are eigenfunctions of the LZ and the L squared operators. What are those operators? We haven't said yet, right? This is where we're getting to by the end of the class. All this stuff in blue that's what we want to end up with. This is going to be the bit we use. To get there, we're going to do what we usually do with problems. You remember the things we do? Define it, calculate the wave functions from the definitions that we restricted to, calculate the energies associated with it, and then figure out what other measurables we can talk about. For this one, these are the other measurables we're going to talk about. Right? It turns out this L squared is going to be really closely related to the energy, so this is kind of getting some idea about the energy and the z component. But right now, that's where we want to end up. So if you get lost at any point today because I'm doing too many thetas and sines and phis, this is where we want to end up. This is the part that we're going to use from today very often. Still good to know where it comes from, how to manipulate it, how to understand it. But this is kind of at the beginning of our next class, this is what I'll write down as the important things from Tuesday. So, preview. Okay, so we have to define some things to get this to work out. So let's start with defining the problem. What the heck do we mean when we say a rigid rotor? Well, when we had a particle in a ring, it was really easy for me to draw. And I'm going to try to draw a sphere. I'm going to try. Actually, let's do it this way. Okay. Okay. There's that, and then I'm going to have Does that look like a sphere at all? Kind of, maybe. No. Let's try that again. Okay. I'm leaving the axes in. Okay. So it's a circle, and then we've got like we've got the three-dimensional aspect to it. You're going to have to use your imagination a little bit. We end up with kind of, instead of talking about it in terms of the x, y, and z, there's an axis coming out at us. We're again going to talk about it in terms of the r, theta, and phi. So our x, y, z coordinate system, we're going to change that to an r, theta, phi. For the same reason we did it for the ring. When we start looking at how x, y, and z changes the particle moves across the surface as it rotates around that origin, it turns out that the r, theta, phi is going to be a little bit easier. We're still going to apply a restriction today. And removing this restriction on Thursday will be what shifts us from talking about rigid rotors to actually talking about atoms. And that restriction is we're still going to say R is constant for now. We'll get rid of that next time. So this is, if we were looking at a diatomic molecule tumbling through space, this is essentially saying the bond length is constant. And it's going to tumble through space with that constant distance between them. We know it's going to vibrate and change a little bit. Approximation. Pretty good approximation. Theta, let's do phi first because we already did phi. Phi is going to be from 0 to 2 pi. In the xy plane, theta is going to be from 0 to pi, moving from z to negative z. Now this is really hard for me to draw, but if we have, right, I don't even have the y-axis drawn in here, but the z-axis, we'd have our phi kind of tilting down this way. If this is z, then that direction would be our, that would be our theta direction. That would be like theta tilting down. Phi is the one that I have a hard time drawing because it's in the xy plane. So it's going to be the one that rotates out of the board, across, back into the board, and around. So I've taken this circle from our particle in a ring, and I've tilted it so it's kind of sticking in and out of the plane away from us. Let's see. I see faces that are not happy. Okay. So this ring is now taken and twisted, so it's kind of pointing in and out of the board. Now we've got this z component as well. So the phi is spinning around in the xy plane. Kind of works out that my water bottle's broken right now. Right, so phi is spinning around in the xy plane. Theta is tilting around. And between those two angles, with these restrictions, we can get to anywhere on the sphere. Right, because I can move to any phi, and then I can swing up and down anywhere along that arc. And then I can swing to another phi, and I can swing up and down along that arc. So we can get to anywhere on the sphere using this. Now, our Hamiltonian, okay with this so far? Did I clear that up with my twisting? Okay. Our Hamiltonian is going to take into account this idea of rotating through space rather than just moving along a line in space. And what that means is we're going to use something that's a little bit new. We're going to use this L squared, this angular momentum operator. We could imagine some point in the not too distant future having a potential of r theta and phi added in there as well. That's going to be if we want to include some sort of molecule interaction. For now, we're still going to leave this as 0. We're going to say there's no potential yet. We just have a thing that's rotating in the xy plane and kind of tumbling through the z plane as well, so it's just tumbling through three-dimensional space. But it doesn't have any force pulling that rotation in any direction. Question?
Why were we able to sort of get away with using the linear momentum operator on the ring, but not in the sphere?
We didn't really use this linear momentum. Oh, okay. The real answer is because when we restricted ourselves to just two dimensions, we end up, this operator here ends up being the LZ operator.
Okay.
So it turns out we've been using the Z component of the angular momentum, but I haven't called it that yet. So we're about to see how it's like, oh, we've actually already been doing this. We just simplified it because we were in restricted space.
Okay.
Good question. Other questions? Okay, so how do we see that relationship? Okay, so this L squared is a total angular momentum squared. That's going to be looking at our Lx component squared plus our Ly component squared plus our Lz component squared. And the question becomes, well, what are these Lx, Ly, and Lz? What is this idea of angular momentum? And I'm going to try to draw a picture of this. So we can imagine if I'm out some x distance from something and I want to make it rotate, I put some force on it in the px direction, sorry, py direction. Right? So if I'm out in the x direction, I put some force on it downward, it starts to rotate if I'm fixed at this point. The problem with that is you immediately switch off of the x-axis, and now you start doing motion into the y direction. And you're going to have some y component show up with force kind of pushing it in the px direction. So you end up, if you're just on the x-axis, you can put force in one direction, and that causes rotation. But as soon as you start causing that rotation, if you want to keep that force going, you now have to push in the y direction as well. So your momentum actually ends up kind of creating this circular pattern to it. Now there's a way we write this down. There's a couple ways we can write this down. The simple way is to say, if I'm rotating around from the x to the y to the x to the y, cross products, 1 through 5. 1s and 5s and 0s and 2s. Okay. So do you know the right-hand rule? Like, this vector and that vector makes something going that direction. Right? That's all we need for cross products right now, right? If I do x and y, that gives me some z direction. That's it. Right? So cross it around. So the way we can write this down, if I wanted to take into account this idea of as I shift away from the x-axis, I shift into the y-axis, this is going to give us some amount of angular momentum pointing along the z-axis. So we call this LZ, which is going to be that x and p part minus the py part. As we shift over to the y part, we take that part off. And as we rotate around, we'll end up going all the way from being in the x-axis to the negative y-axis, back to the negative x-axis, back to the positive y-axis, and we'll just keep rotating around between those different parts, from one to the other, one to the other. This comes from, again, cross products. I saw there was a lot of people who don't know cross products. So this idea of angular momentum comes from taking the radius vector crossed with the momentum vector. Taking a radius and then just rotating it about by doing that cross product and seeing where it moves to. I can't tell if those are happy faces or disgusted faces. Could be both. We can go through this over and over again, so we can write down the same type of thing for Lx and Ly, where we're looking at how does something rotate. If we're looking, this is looking at the xy plane, giving us z component. If I looked at the xz plane, that would give me the y component, and then I could look at the zx to give me the y component. Right? I can look at each of those dimensions, and I can essentially get some angular momentum pointing along each of our Cartesian axes. So I can look at angular momentum things, something rotating around in space, if I wanted to understand how that rotational energy behaves. Right? It's not just linear momentum anymore, it's some connection of the x component and the y component, and how that position and that momentum relate to each other, not just in the x direction, but also in the y direction. Okay. We're not going to worry too much about the cross products right now, but I will write down. Let me rearrange this real quick. I'm going to put this up here and this down there. So angular momentum is going to be that r vector cross that p vector. You guys really don't know cross products?
Mathematically, yes. Conceptually, no.
Okay. I might do, depending on how long I take with this, I might do this at the end just to show you. We'll see. Because it's going to come up again. So we'll see. This LZ is going to be that x py minus y px. Now, as we saw with the particle in a ring, we said, look, doing this in the XY components, it's easy for me to understand because I've done Cartesian coordinate systems my whole life up until now. But when we start looking at the differential equations that come out of this, they get messy pretty quick. So we can rewrite it, and it's actually less messy. You might not believe me, but it ends up being less messy when we rewrite it in spherical coordinates. For the LZ, it does end up less messy. If we translate this to spherical coordinates, this one is going to end up being IH bar, negative IH bar, because the momentum piece is there, d by d phi. And it turns out, the question that we had just a moment ago, when we were looking at particle in a ring, we were really doing our LZ, angular momentum operator. Right? We've got the IH bar d by d phi. We square this, we're going to get the negative h bar squared d by d phi squared. So when we did the particle in a ring, we were actually already doing orbital angular momentum. We kind of skipped over this idea of how we write it in terms of the x and y components because we had some nice constants going on because we were restricting ourselves to a ring in the xy plane. Okay, so that's LZ. I'll show you LX and LY real quick as well. Right? And these are things that we are going to be aware of. LX operator would be, again, another cross product. It's going to be YPZ minus ZPY. That's on everything. And when we rewrite this one in spherical coordinates, it doesn't look as nice as the Z component. This one, and I'm going to have to give myself a little bit more space for that. When I rewrite this one, I'm going to get the negative IH bar up front because I've got momentum again. I'm going to get negative sine theta, d by d theta of sine theta, d by d theta, minus cotangent theta. Oh, I still didn't give myself enough space. Cosine phi d by d phi. You don't necessarily need to write that down. We're not often going to be using it in this form. But this is the operator. So we're going to have some nice tricks that we're going to use with these operators. I just realized I could have put in our things to know from today. And we're going to get something similar when we do the LY. Question?
What determines which one is negative and which one's positive?
For which part? For the Cartesian?
And LX, we have the x and y components for LZ. Which one, why is y negative in this case? Just because it's going down. And then for LX, why would the z component be negative?
Well, so when we look at this, when we have the y negative, it's just a matter of where we start, right? These are going to rotate into each other and kind of just give us the same thing back and forth. So we typically do this starting with clockwise rotation cross product. We could do it the opposite direction and flip the signs. But we're just going one direction. So these sign conventions come out of the definition of the cross product. Should I do the cross product?
I guess I'm just confused for LX though.
Why is it YPZ minus ZPY?
Yeah.
Okay. Okay. Let's do it. I'm gonna show you. We have to remember how to do cross products then. So when we look at the cross products, let me find my little picture here for this. There it is. Okay. So when we do cross products, I'm going to go ahead and just erase these notes here. We're going to do a quick little cross product aside to remember why this thing happens. So if I want to do the L vector, as the R cross P, we can essentially set this up as a right, so this is like IJK directions. Have you seen that notation before? Okay. And then we're going to have x, y, z, and we're going to have px, py, pz. And I want to find out, well, what happens to my I direction when I do this? So my I direction, which would be like my, let's do our z direction first, because that one's what we already have written on the board. If I wanted to do my z direction, one look and he's like, right, if we wanted to do our z direction, we're going to be looking at this little section of it. And we're going to do xy minus yx. Is that familiar to anyone?
Yeah, honestly,
Yeah.
Okay. Some people are starting to remember, right? Cross product. So if I wanted to look at my k direction, which we usually use for z, I is like our x, y, z, but we need different variables so we don't have too many x's. I could have put like my x unit vector, my y unit vector, my z unit vector. That is going to be x py minus y px. It's that cross product of how I take position and start rotating it around as a cross product of two vectors. Now it makes sense? Cool, okay. Now if we did the same thing for the x, I'm using too many colors, okay. So I'm going to take that out. Keep the colors consistent. Now if I want to do the same thing with my x over here, I'd be looking at my y and z portion, and I'd have ypz minus zpy for my cross product. Taking two vectors, crossing them into each other. So that's where the negative signs come from. So my I hat, or my I vector, ends up being ypz minus zpy. And again, I'm not putting hats on these because we can do this with classical vectors as well. This is just generally classical or quantum mechanical. We can treat it that way. If we wanted to, the whole point of this is if there's a classical version of it, we can make a quantum version of it. Right? So if I've got this classical operation of angular momentum in the z direction, I can make a quantum analogy using my operators that relate to it, my Hermitian linear operators. And then we rewrite into spherical coordinates. One more to do. I didn't need nearly as much space as I thought. That's good. Our Ly hat is going to be the same type of idea. Order on all of this is really important. One of the things that becomes really critical, because we are going to do operators acting on functions, we have to make sure, and that's why I'm checking my notes to make sure I don't mess this up, we have to make sure we get the order of things correct. So this is going to be zpy minus ypz. And generically, I cannot flip the order of those operators. Right? When we are doing this, when we're switching from just multiplying numbers together over here to now doing operations, that order becomes really critical. Because keep in mind, those py's and those pz's, those are derivatives with respect to y and z. So if I change the order, I'm going to change what I get. If I put py before p, actually in this case, I think we're mostly okay. But if we change those orders, it might mess things up. Now, again, we switch this into spherical coordinates, and we get some nice parallels. Question?
Why is it y and not x?
Because I messed up. It's supposed to be x's. Thank you so much. It's supposed to be x's. So please fix that in your notes. Thank you for catching that. That would have been terrible. I probably would have realized in like 15 minutes and been like, oh, hold on. Yeah, so if we're looking at the y direction, it's going to be that z and the x crossing to give us the y. Thank you. Please catch me when I make typos.
I wouldn't know.
That's fair. So catch me if I make a typo in this next part. I'm joking a little bit. IH bar Oh my goodness. I have such a bad typo. This whole thing, this is the next part. This is for L squared, not for Ly. So put a circle around that in your notes. We're going to need that in just a moment, but I actually had a terrible typo there. I was looking at the wrong page. It's not nearly as bad as it looked. And I should have realized I had a mistake when I did this squared, right? If this is just linear, I shouldn't get squared yet. So I should have seen that mistake. Question?
Is it cosine of phi and d theta?
Yes.
Okay.
It's cosine phi d theta minus cotangent theta sine phi d phi. And then this one, it's not. Hold on. I wrote L. Okay. I'm just getting my X's and my Y's confused. Okay. Double checking. Sine phi d by theta minus cotangent theta. Okay, cool. And the reason that that's important is because we have some parallels. Right, we end up with parallels between Lx and Ly, where they're related to each other. If you remember, was it cosine is the near one over the hypotenuse? Sine is the far one over the hypotenuse. So it's like x over h, right? So it turns out these cosine and sine terms, relate to whether we're looking at x or y. So when you switch between the two, you switch which direction you're looking at it. Now, all of that's fine and dandy. The thing that becomes important, are you ready for the important thing? Question? No, what's up?
I have a cross product question.
Sure.
Why wouldn't it be xpz minus zpx? Because we've been going to the right first and then to the left when we're cross producting.
Let me see.
Or,
The middle one has the sign flip. Remember? Positive, negative, positive. I freaked out for a second. I was like, please don't make me make another typo in this. Positive, negative, positive.
Positive, negative, positive.
Okay. If that's not making sense for you, that's okay. Mostly, maybe review your notes from the past a little bit, not this class, your other classes. Let's look at what L squared looks like, because again, this is all just doing the setup, so we can try and figure out, right? Our setup is we're restricting ourselves to this three-dimensional sphere. We want to figure out how does an object rotate around in three-dimensional space. How can we talk about the energy associated with that? How can we get wave functions associated with that? That's the main thing. This is all just defining the problem. And the thing we're really going to be looking at is we want to solve the Hamiltonian, this thing, right? So really, all of this was so we could look at L squared. So what does L squared look like, and how can we use L squared to get some function to explain what's going on? I'm going to erase my cross product thing. Okay. So L squared is going to end up being negative h bar squared, right? Because the I is going to get, the negative I gets squared and becomes just a negative 1. And this is the thing I erased that I had written down just a second ago. 1 over sine theta, d by d theta, sine theta, d by d theta, plus 1 over sine squared theta, d by d phi squared. That's our LZ operator. And here's why it's really nice to write that down. Because someone else has already solved it. Right? In the past, what we've done, when we were doing the particle in a box, we said, hey, we can kind of look at this differential equation and have, like, just kind of know what things work because we have some math experience. When we looked at the particle in a ring, we said, hey, we can just kind of know what things are going to work because we've got some math experience. When we looked at the harmonic oscillator, we were like, ooh, we can kind of get part of it. But it turns out the harmonic oscillator, there was this set of functions that worked well with that operator so we could have more than one answer. And it turns out with this thing, we're also going to have a set of functions that give an answer to this. Question?
Is it 1 over sine d theta times sine theta?
Yeah.
Isn't that just...
No.
No?
Because we have to, so once we do, and this is because operators,
Oh, that's
right?
Okay, yeah.
So we're going to have to operate on this and then apply the chain rule.
Okay, that's my view.
Or the product rule, not the chain rule. Chain rule is something else. I ran down a rabbit hole with that the other day. So we're going to have to apply it to like d by d theta of psi and then do the chain rule across. Product rule across. Let's do it again. So yeah, it actually is sine sandwiched by 2 d by d thetas on purpose. So we can go ahead, we can set up our Hamiltonian with this L squared. Now there is a shortcut to writing this down. You'll notice over here there's a couple nice parts. Our LZ part is in there, right? The d by d theta, the d by d phi squared that we had for LZ. That part's tucked in there already. So that's going to be in there. There is also a way that people write this down. This whole chunk in here gets this funny symbol because people just get tired of writing it down over and over again. And this is called the Legendrian. The solutions to it are the Legendre polynomials. All old French mathematician, right? That's why it's got that name. So what we do is we can say, okay, stop looking at the wrong pages. Okay, so we can say, I'm just going to write it down again. Our Hamiltonian is going to end up being negative h bar squared on 2I. I'm just going to write it down again. 1 over, no, I'm not, yeah, I am. Sine theta, d by d theta, sine theta, d by d theta, plus 1 over sine squared, theta, d by d phi squared. So if I have my Hamiltonian operating on a function, right, back to normal quantum mechanics when it was easier. If we just have h psi, e psi, we now can get functions for that Hamiltonian. Not that we're going to come up with on our own. Do y'all know how you would solve it if you wanted to solve it on your own?
Yes.
Guess and check would only get you so far. You might get the first answer. But it turns out power series expansion, right? Power series expansion is the way that you solve these complicated differential equations. We're going to recognize that there's going to be some exponential term because we still have that d by d phi squared. But if we want to get the additional polynomials, the additional factors that go along with this, you do a power series expansion, you get a set of functions. So, and that's kind of the point of this, right? The point was we wanted to find some functions that give us solutions to this equation. Question?
Why do we write it as psi?
Because I was doing it in the most generic way,
Oh, okay.
right? So the functions, we're going to rewrite our psi's as YLMs right now.
Oh.
So it turns out that the way that, by convention, it's YLMs because Legendre, when he solved it, he did it for YLMs.
Okay, thank you.
So we get some normalized solutions. That's not enough space. Okay. Let's do it over here. I'm going to erase my excellent three-dimensional picture of a sphere. Makes sense to everybody. So we have our normalized solutions to it. And we're going to have things like 1 over 4 pi, the 1/2, that's our normalization constant, e to the 0. Yes, that's equal to 1. I just wanted to put it in there for a moment to be on display. Now, you don't need to write these down. You already have them on a handout. So if you're copying all these down, just pull out your handout and be like, oh, yep, there's that one. Oh, yeah, there's that one. If you don't have your handout handy, go ahead and write them down, I guess. But this is just me taking a moment. One more to write down. So we can notice some things about this. Right, from our particle in a ring solution that we did last week, we can recognize that there's a z component here, and that when it's 0, that's going to correspond to the m sub L equals 0. We've got a bunch of those. Here, that's going to correspond to the m sub L equals plus or minus 1. The plus 1 is the positive, the minus 1 is the negative, right? We've got those z components in there as well. Here's another e to the 0. The parts that are out front here, this cosine theta, sine theta, and this cosine theta, this 3 cosine squared theta minus 1, that's going to be kind of the new part that takes into account the tilt from the z-axis down. Right, so we've got our phi parts, we've got our theta parts, and this one's really fun to me. This one I really like. Has anyone, okay, a little weird aside, has anyone heard of solid-state nuclear magnetic resonance? That's where, have you heard of NMR?
Oh, yeah.
Yes.
Okay, have you heard of doing NMR on solids?
No.
You can. So you can do NMR on solids, and it turns out you run into this really quirky problem of if you just have the solid sitting there, because it's a crystalline solid, but all of the crystals are kind of tumbled in different directions. If it's a powder, you get these really broad, weird line shapes. And so what you do to fix it is this thing called magic angle spinning. It's magic angle spinning. And it turns out if you tilt your sample to the correct angle and then rotate it very quickly along that angle, your broad peaks become really sharp lines. And the magic angle is such that this second order term goes to 0. So it ends up being like 57.2 degrees. Because if you plug in the correct angle for this, this term goes to 0, and then you get really nice lines. My undergraduate research was with solid-state nuclear magnetic resonance, NMR with solids. Question?
Is that why the bore width on high field NMRs are usually so large?
I don't know. I will have to ask more questions about that, because normally you try to get your bore width as small as possible to have field homogeneity, but it's a balance between probe size and how many electronics you need to fit in versus field homogeneity. With high field magnets, with the stronger magnets, you have, depending on the quality of the magnet, you'll have higher field homogeneity, so you can essentially make your bore wider and then you can fit more materials in there. But typically you always go as small as possible for your bore. That was an NMR aside. I'd love talking about NMR. I could talk about it for ages. So point is, we've got, and I didn't write all of them. Guess how many functions there are? Infinite number, right? L can go from 0 all the way up to whatever. M sub L in this situation now becomes limited. I forgot to write this down before. M sub L, ooh, maybe I'll have you do that. M sub L now becomes restricted. I'll show the other board in just a moment. M sub L now becomes restricted. When we did the particle in a ring, M sub L could go on forever. When we're doing the rigid rotor, M sub L is limited by our L value. So if L equals 0, we only have M sub L equals 0. If L equals 1, M sub L could be 0, plus 1, or minus 1. If L equals 2, M sub L could be 0, plus 1, minus 1, plus 2, minus 2. On and on and on. But we've got these restrictions. We can have a whole bunch of wave functions. But there's a nice thing. There's two really nice things that we're familiar with now, hopefully. Right? And the way that we label these things, right? We label these things, these normalized solutions are Y M sub L superscript, L subscript. You'll see it written down with different formats in different books, but I'm pretty sure this is the format your textbook uses. I was looking at like 3 different textbooks the other day. But here's what's nice. If these are normalized, notice these are imaginary functions, so having that complex conjugate in there is really important. What's this integral equal to? Okay, yeah, so this is equal to 1. Because they're normalized. And then we've got another function we can write down. If L prime and L are not the same number, zeros. Zeros. Orthonormal basis set. So it turns out we don't have to look at these functions very often because we understand orthonormality. I hope. Yes? A couple big grins. I think those grins are agreement. I'm going to go with grins are agreement. Yes? So it turns out all of this, once we have these functions written down, we can just use this notation. We can just say, hey, if the M sub L's are different or if the L's are different, I'll be in this situation where I end up with a 0 integral. Because our Hamiltonian is a Hermitian operator, so they're going to be orthogonal functions. If it's the same function, I'm using my normalized functions, the integral is always going to be 1. So as long as it's the same functions, I get 1. If they're different functions, I get 0. That's going to simplify our integrals. We don't really, there's a few problems in the homework that I know you're all doing that ask you to prove that they're orthonormal. So it actually asks you to go through the process of like, do these integrals show that they're orthogonal, show that they're normalized? I could ask you to do that too, but we already know what the answers should be. That's the beauty of having a normalized basis set for a Hermitian operator. Okay. Okay, so this is a lot of math to get to. This thing's equal to 1, this thing's equal to 0. Question over here and then up here.
If we weren't given the function as normalized, we would have to solve for the one day.
Yeah, so we could also solve for the normalization constant by requiring function star times function using the same function, requiring that to be equal to 1. We could get this number out front here. I'll mark these real quick. Right, so we've got our z component, we've got our xy component, and then these numbers out front, those are our normalization constants out front. Right, so 1 over 4 pi to the 1/2, 3 over 4 pi to the 1/2, 3 over 8 pi to the 1/2. Those are our normalization constants. Question?
So for the Lx and Ly operators, are those like given to us, or are we supposed to memorize them? Or
Definitely memorize them. No, I'm kidding. No, we're going to have a couple tricks where we say, hey, we're not going to really use those. There's one more thing I want to write down. Where am I going to fit this?
we don't use them because we like go to the next step.
Kind of. So it turns out, I'm trying to figure out the order I want to do this in now. Maybe I'm going to change my order a little bit. So it turns out, over here where I said we're going to get to in the end, we used LZ and L squared, right? And I didn't say why I used LZ and L squared. But it turns out, whenever we're trying to define a system, and we want to do it with as much accuracy as possible, there's a special phrase we use, which is the maximum set of commuting operators. You remember the Heisenberg uncertainty principle? So if two operators don't compute, there's some guaranteed uncertainty in it. We're going to want to have, if we want to optimize our system, we're going to find for these functions, what's the most operators we could use that all commute with each other so we have no uncertainty in it. And it turns out, when we start looking at Lx and Ly, these things don't commute with each other. So Lz, Lx, and Ly, they don't commute with each other. That means we're just going to pick one of them and go with that, rather than using all of them. So what does that look like? The short answer, where can I put this? I'll put it here. This is one of the important things I could have done over here as well. The short answer is L squared and Lz. If I look at the commutator of L squared with Lz, they commute. They just go away. Right? I can do them in either order. I could have written this as Lz, L squared, Lz. These commute, so both directions work totally fine. I can know both of these components, no problem. The catch is, I'm going to do it up here. If we looked at Lx with Ly, if I look at the commutator of Lx with Ly, any predictions what we're going to get? Non-zero, thinking cross products, x cross y? Yeah. It turns out you get x cross y gives you z. Our operators behave in that same kind of way. Then if we did, again, getting the order correct matters here. If we did z cross y, you get Lx. And if you did z cross x, you get Ly. They don't commute with each other. They rotate into each other. And this should make some amount of sense if you start thinking about rotating things. If I'm in X and I start rotating around, I'll get to Y. If I'm at Y and I start, if I'm in X and I start rotating around, I'll get to Y. If I'm in Y and I start rotating around, I'll get back to X. If I'm in X and I start rotating around a different angle, I'll get to Z. And back to X, back to Z. So it kind of makes sense that this angular momentum, they rotate around into each other. Right? I erased it, but that cross product idea of one crossing into the other, crossing into the other. Now what this means for us is there's some relationships we can use to talk about Lx and Ly and the ways that they don't commute. But if we are going to talk about measuring a system, we're going to go for the maximum set of commuting operators. And we could have, honestly, we could have gone with Ly and L squared. But people, when they were first doing this, they looked at that equation versus that equation and went, yeah, let's do LZ. Picking between this one and that one, LZ. Now, which direction is Z is completely arbitrary, right? When we have a molecular system, we look at our molecule and we say, we often say, I'm going to call the distance from the first atom to the second atom along the bond is my Z axis. Because we have to define what the axis system is on our molecule. We usually pick along the bond for Z, because that's going to be the simplest rotation. Question?
This is probably a silly question, but why can you go Z then Y to get X if it's right-handed?
Funny you should ask. It has to do with the negative, like with the definition of these momentum operators having that negative I, having that IH bar in it.
Okay.
And I've got a handout so you can prove it. Eventually, we'll work on this. So yeah, this is a rather lengthy proof. Not necessarily difficult, but lengthy. Question?
I think I might have just missed it. Why are we saying that e to the 0 is like the Z component in those normalized solutions?
So if you remember, so we have this d by d phi term, which gives us e to the im phi. And so whenever there's no, so actually if you look on your equation sheet, they probably just have nothing there. Right? E to the 0 is equal to 1. So that's when m sub L equals 0. You just don't put anything there. I put it there explicitly so you can see, oh, there is a Z component. It's just the Z component's equal to 1. Right? Because e to the 0, that's just the same as writing 1. So those cases, this e to the 0, e to the 0, that's because m sub L equals 0. Those terms, we don't have those written down on the equation sheet. Other questions? Okay, so we talked about commuting operators. The last part, I'm going to bring this screen, I'm going to bring the camera back over here for a little bit, because we're kind of at the end of things, right? So what have we done today? Right, we did a bunch of kind of rewriting our problem into this different coordinate system, realizing that we have to think about, if we're talking about rotation, we have to talk about how x and y relate to each other as they move through space. And we said, I can write down a Hamiltonian in terms of that angular momentum. If I go ahead and now I've got some functions I can write down, then we write them down instead of writing them as psi's. By convention, we write as y with a subscript L, superscript m sub L, solving our theta phi part. No r part yet because we said r is constant. And if we operate our Hamiltonian on this, we get certain energies. If we just operate L squared on this, we get our function back, right? This is going to make it easy for us to calculate average values as long as we've got eigenfunctions of the operators we're looking at. So we've got energies associated with this rigid rotor now. We've also got a z component and a magnitude component, right? L squared is like Lx squared plus L squared, Ly squared plus Lz squared. That's going to be like a full magnitude. Now, what this is really interesting, the reason I get really excited about this is because this gets us another piece of the spectroscopy puzzle, right? We've had, there's two parts to the spectroscopy puzzle so far. Right? The vibrational part, that was IR spectroscopy. If you were doing the problems in the textbook and kind of following along with those, you find that the energies and wavelengths associated with the vibrational work we did 2 weeks ago, it ends up being in the infrared part of the spectrum. As you start to work on problems with this h bar, that I being reduced mass times r squared, it turns out that rotational spectroscopy that's going to be on the microwave energy scale. So it's a smaller energy scale than the vibrational. I like to draw a kind of picture associated with this. Right, the vibrational is going to be a bigger energy, the microwave is going to be a smaller energy. So if I draw a vibrational, kind of our typical harmonic oscillator, right, and I could keep going, I just ran out of space here. You could keep going. This difference in energy between these two right, that delta V equals plus or minus 1, that gives us the vibrational spectroscopy. That gives us IR spectroscopy. So we can look at bond vibrating. You all have done IR spectroscopy at this point. A whole bunch is really useful. Lets you figure out what molecular structures are made, like what the molecular structure is, by looking at those different bond vibrations. We can explain it with the vibrational spectroscopy. Has anyone done rotational spectroscopy? A little less common. It turns out that rotational spectroscopy, this V0, in addition to having that vibrational mode, is going to have a bunch of small rotational answers on top of it. So that's going to be the rotational part. And it turns out each of these, so at the V equals 0, the V equals 1, we've got this rotational aspect on top of it. So when you get to lower and lower energies in your vibrational spectroscopy, your IR spectroscopy, it starts getting really messy because you can get down to low enough energies that you start picking up these extra splittings. And so it looks like a total mess because you're not just looking at the bond vibrating anymore, you're also looking at the rotation about the molecule's center of mass, the mu. So you're picking up that extra information. If we don't want that extra information, it's just totally in the way and we try to avoid it. But we can also use that extra information to understand what's going on with the reduced mass or the different bond lengths associated with the material as well. We'll start, the homework problems we start with, we're looking mostly just at diatomics, right? And we're looking at how diatomics rotate, and we can talk about how much energy it takes to kick something from a lower rotational state to a higher rotational state. So if I wanted to, as this thing is spinning, how can I make sense of it? Or we can do the reverse, whereas if we have the rotational spectrum, we can use that to find the moment of inertia, the reduced mass, the radius of the material. If the radius was like an average radius fixed, right? But we can use this kind of in both directions to get physical information about the material or to understand what that material's spectrum is going to look like. So that's where this is kind of, for me, this is where the quantum mechanics starts to become really practical, is because we know IR spectroscopy. We don't know rotational spectroscopy as much, but we can use rotational spectroscopy as well. We can start to understand how energy is interacting with molecules. There's another piece we need to add on to this. So we've got this vibrational state. It turns out we've got another vibrational state. And that's when we start to, like, for our rotational and for everything we did today, we had the radius as fixed, rigid rotor. The rigid part means the radius is stuck. Next thing we're going to do is say, well, what if that distance wasn't stuck? What if that distance could change? What if we had an R component on top of this? Now, as I'm sure you can imagine, it adds extra terms inside of this thing. And so it looks extra gnarly. But we already know solutions to the angular part in the spherical harmonics. We're just going to add it turns out we just have a radial part, so all that's going to happen to these functions is we're going to have a radial term multiplied on top of it, because we can do separation of variables. And technically, the reason this worked out this way is because we can rewrite. I really want to send you this thing. There's it turns out I got really frustrated when I was looking at the textbook this weekend because I was like trying to find something that really explained why these M sub L values were restricted this way. And the textbook said, oh, just have your students download this extra file on the online textbook. I was like, it's like literally like a half page of information, and they were just like, make you go to the website and download it. But they also do this part there. You can write this y M sub L right, so it turns out that the way that this gnarly equation that we wrote down, this Hamiltonian, was solved, was saying, hey, I can split my theta terms from my phi terms and essentially solve for like a theta function and a phi function. And then I just multiply them by each other, and that gets me my theta component and my phi component. When we go on Thursday to do that with the radius, we're just going to have an r component on here as well. So it's not going to be like solving, it's going to look like a really different problem, but it turns out it's same solutions with just an extra piece multiplied on it. I went a little bit out of, okay, 10 minutes, I can do the last weird thing. Deep breath. So the uses of this are going to be, like with all of this math, the way we use these things is going to be pretty straightforward because we've got that orthonormality. And these operators, since these are eigenfunctions, and they're eigenproblems, we're going to get the same functions out, and so we can use orthonormality if we wanted to know like average L squared, average LZ squared. That's all going to be okay to do because we're going to have orthonormality there to help us out. The only place where it starts to get really tricky is if I say, hey, tell me the Lx value, and you have to be like, it's not an eigenfunction. Like, our functions are not eigenfunctions of Lx and Ly. We can still solve for the averages, but it turns out there's another kind of visual way we can think about this. And it's kind of buried in this piece here of LZ versus L squared. What am I going to erase? We'll do this. Done with that part. I'm going to skip. Yeah, you can get rid of the functions too. You have a handout for those. So one of the quirky things that happens here that you might not have noticed because there's a lot going on today is M sub L will never equal L times L plus 1. The z component will never equal the magnitude. How can that possibly be true? If we think about, some rotating vector, right? If M sub L is 0, I'm going to be pointing along the not z-axis, right? If we have this as the z-axis for now, here, if I'm in the xy plane, my z component can be 0. My magnitude is still not 0. Or, right, if I had, even if L equals 0, my L times L plus 1 would be equal to a vector length of, it would be like 1. if I did it for if L equals 1 and M sub L equals 1, L equals 1 would be a vector magnitude of length 2. But my Z component here, what colors do I want to use for this? So if that vector is length 2, if I just looked at the Z projection, it would have a length of 1. It wouldn't be the full length of it. Question?
Is the L equals 0, 1 necessarily correct? Because 0 times 1 is 0.
Oh, shoot. You are absolutely right. Okay. I felt so good about that. What did I do wrong? Okay. So in the L equals 0 case, I guess they can be equal to each other. That's 0 magnitude. Oh, and I just erased the functions. That actually does make sense. Because when you're in the L equals 0 case, wait, do I have a mistake? I double checked this. What times L plus 1? Oh, right. Okay. I always get worried when something has 0 energy, because 0 energy is a trivial solution typically, right? 0 energy means the thing doesn't exist. The reason we had 0 energy when we did the rigid rotor was because we were restricting ourselves to be on a ring. And so we're like, oh, we can have 0 energy in that case because we've got these fake constraints to it. The same thing is happening here with the rigid rotor. We're like, oh, radius is constant still. So we still end up with a situation where you can have 0 energy because of that fake restriction on top of it. So in the 0 case, it's like you don't have any angular momentum, so I shouldn't draw any picture for that. Let's do it for these two. Let me fix that. Thank you for catching that. Trying to fit too much in at the end of class. Let's do it for the L equals 1, M sub L equals 0. Right, in that situation, that's where we've got an L component, so we've got some angular momentum associated with it, and there's no Z component associated with it. If I do my projection onto the Z axis, I get nothing. If I'm in the, and I don't like doing it in this order, I want to switch the order of that as well. If I'm in the L equals 1, M sub L equals 1, I've essentially got this component that's pointing up along some direction, not completely along the Z-axis, something along the X-axis. But we already know that we can't know the X and Y components. So how do we take into account this uncertainty of the X and Y? If we know Z and we know L squared, we can't know X and Y. And what happens, the way we explain it, is we say that there's essentially a cone of possibilities. So it's like a vector. We don't know where it is in the xy plane, but we know it's someplace along this cone. So this vector could be someplace, I didn't draw that cone perfectly well, but there's some place, this vector is going to essentially make a cone of where it can be. Its z component is known, its total length is known, but we don't know the x and y component of them because of that uncertainty idea. And you'll see that picture, they've got a nice picture of that in the textbook as well. Questions?
Just to make sure on that axis the z is up and down.
Yeah, let me put labels on that. I'm really bad at drawing these in 3 dimensions. It should be same thing. For this one, it's x. This one would be like our particle in the ring almost, right? Where I've essentially got some rotation in the xy plane. So I'd have my vector. Oh, no, this is not the same. Sorry. I have some vector going across in the xy plane. So it's spread out in the xy plane because I know my z component is 0. But I still can't say specifically both x and y components at the same time. Okay, with that, it's quite important that you work on the problems for the rigid rotor. Make sure you're reading the examples in the textbook for the rigid rotor. This is the end of chapter 7, because what happens on Thursday, we throw this radius component in there, and all of a sudden we're talking about the hydrogen atom. So we're finally, week 5, going to talk about atoms. Questions? Yeah, okay, here, let me stop recording that.